In this video and the next, we're going to be looking at the Lambda-type Three-level atomic schemes and some really cool things that we can do with it. The idea of using an ensemble of such atoms to store optical pulses was first reviewed in detail in 2007. So here I've drawn an energy level diagram of an atom with the states that we're concerned about. In this configuration, we consider two ground states of an atom that have a long lifespan and an excited state that is accessible to both the ground states. I'm going to call the ground state with lower energy ground and the other ground state as an auxiliary state. So the idea is that we use a strong electromagnetic field that we call the control field, coupled to the auxiliary and excited states to manipulate our system. Then we couple a weak probe field to the ground and the excited states that contains our quantum information. Since we don't care about the quantum information in the control field, we treat it classically. Therefore, the atom is interacting with two photons at the same time. The capital delta here represents the frequency difference between the atomic transition and the probe frequency. The little delta here is the frequency difference between the probe field and the control field. This capital delta is called the one photon detuning, and little delta is called the two photon detuning. Another important thing to note is that the transition between the ground and the auxiliary states are forbidden and cannot take place. We can comfort ourselves knowing that we've already separately studied the two parts of the system. If we isolate these two parts, on the left we have a quantum field interacting with a two-level atom, and on the right we have a classical field interacting with a two-level atom. So let's first look at the interaction with the quantum field. In the lectures, we've already seen Pauli matrices and rising and lowering operators, and these are useful when discussing the Hamiltonian of the system. We've seen this before. The total Hamiltonian will comprise of Hamiltonian of the atom, light, and the atom-light interaction. The Hamiltonian of the atom is pretty straightforward. It's the energy of the atomic states. The Hamiltonian of the light is also pretty simple, which is just the energy of the photons. This is the number operator. A here is the annihilation operator, A dagger is a creation operator for photons. The atom-light interaction term can be derived assuming that our atom mostly interacts with the field as a dipole. This term here represents the de-excitation of an atom releasing a photon. This term here represents the excitation of an atom absorbing a photon. G here is the coupling strength. Recall that we had also used the rotating wave approximation in deriving this. Together they form the James-Cummings Hamiltonian. Now, if the coupling strength between light-atom interactions is significant, then we can no longer describe our system as separate states of light and atom. If you write our probe field in the number notation, then our combined atom-light system can be described in this tensor product basis, and the interaction term will couple all of these states. The eigenstates of our Hamiltonian are now called the dress states. The energy difference between these dress states is proportional to the Rabi frequency, so this is in turn proportional to the coupling strength and the one photon detuning. Therefore, if the coupling strength is larger, it will have a bigger effect on the system. Now, getting back to the bigger picture, our probe field contains the quantum information that we want to store, but it's not really intended to affect the system itself, and that's why we try to have a weak coupling. Now on the other side, a control field with strong coupling is used to modify the system, and this affects how the probe field will interact with the system. However, note that the quantum information in the control field is irrelevant, and thus we can use a semi-classical approach for the control field where we treat the atom as a quantum system, but light as a classical system. The Hamiltonian of this system will simply be where we've now ignored the Hamiltonian of light. The difference now is that the Hamiltonian for the interaction term on the left-hand side was given by this dipole operator inner product with this electric field operator, which describes our quantum field. But on the other hand, we will still have the dipole operator, but this time we'll have a classical field and not a field operator. Where since we're only talking about the system on the right-hand side, I've dissolved the capital delta and the little delta into this delta prime. So in this case, we want the coupling strength of the Rabi frequency to be strong. And again, we can look at the dress state picture and we want to manipulate the behavior of our system. Note that we've made a subtle assumption here that we're using lasers and that single optical mode is coupled to our atoms and the rest are in the vacuum. When we're driving our atoms with these optical fields, there's a competing process called spontaneous emission, in which our atom undergoes a spontaneous decay from the excited to the ground state and a photon is released. If we consider our system to be a single optical mode coupled to the atom, then the environment can be considered as a collection of all the vacuum modes. And we can see that the spontaneous emission couples the system to the environment. If we treat our environment to be Markovian, then we can use the master equation formalism to describe our system. So this will be the evolution of our identity matrix. Capital gamma is the rate of decoherence due to spontaneous emission, and the Lindblad superoperator can be written in this form. Now, because of the spontaneous emission, we can say that for weak driving fields, our atoms will predominantly be in the ground state. That is, we can make a pure state approximation. Using this, we can simplify the off-diagonal terms to give us the evolution of coherence between the ground and the excited state. And omega tilde here in general just represents the coupling strength of our field. Now that we've spent a few minutes refamiliarizing ourselves with the two-level atom, the big question is, what if we consider these interactions together, and what if we have an ensemble or a collection of these atoms? We will discuss this in the next video, so see you there.